Hi guys, and welcome to day 3. This is your last day of probability, and the good news is that we're not really learning anything new today. It's mostly going to be a review day, so there's going to be a lot of pause the video and try this example, or me just continuing to proceed through the examples. Feel free at any time to pause and work through things on your own and then check your answers, or to go back and rewind if you want to hear an explanation again. So here we go with conditional probability, and we're starting off with a warm-up example that is entirely review. So here's your first chance. Go ahead and pause the video, do all of this page, except for the very last question on the bottom, and when you're done, come back to the video and we'll go over the answers. So the example is about students at a particular university and the kinds of computers that they use, and whether they're undergraduate or graduate students. So parts A and B, depending on how you set up your table and your Venn diagram, it could look pretty different from mine, but the numbers in your representations should be the same. So part A was to make a two-way table for this particular chance process. Now mine looks like this. Depending on whether you put undergrad or graduate student on the top or the side, or Mac or PC, or the order that you chose to put the categories in, again, it could look pretty different, but you should still have those same numbers in there. Part B is to use a Venn diagram to represent the exact same information. Again, depending on what you chose to be in your circles, it could look pretty different from mine. I chose to have one circle represent those that owned Macintosh computers and one circle to represent, graduate students. If you chose PC and graduate student or PC and undergrad, or like switch the order of the circles, it could look pretty different again. But those numbers should be pretty much in the same places. Part C, what is the probability that a randomly selected student uses a PC? So I'm going to take the number of students that use PCs out of the total number of students. So I would end up getting something like this. The probability that a random person uses a PC is going to be 6,000 out of 10,000, which comes out to be 0.6 if you like decimals. Part D, what is the probability that a randomly selected student is a graduate student who uses a Mac? So they are a graduate student and they use a Mac. So I'm going to take the number of students who are graduate students and use max out of the total, and you should get something like 10%. Again, if you give a proportion, if you give a percent, if you give a fraction, all of these things are okay. Part E, what is the probability that an undergraduate student uses a Mac? This is the first one that's going to be slightly different because you already know that they're an undergraduate student. So it's out of those students who are undergraduate students, what's the probability that they use a Mac? So the thing that's different is going to be my denominator. I'm going to choose the number of those that are undergraduate students and use Macs, but it's not out of everybody, it's just out of the undergraduate students. So the probability that they use a Macintosh computer, given that they're an undergraduate student, it's going to be the 3,000 students that have Macs and are undergraduate students, out of the number of undergraduate students. So it's going to be 3,000 out of 6,700, which gives you a number that's about 55%. And the last one, what is the probability that a PC user is a graduate student? So you already know this person uses PCs, and there's 6,000 of those. Out of those 6,000, what's the probability that they are a graduate student? So I'm going to be looking at the number of people who are graduate students and PC users out of just those that are PC users. And you should end up getting something like this. What's the probability they're a graduate student given that they use PCs? And you get a number that's about 38%. Now, nothing in this is new. You should have been pretty comfortable with all of these. If you're not quite comfortable with the symbols yet, you still have a couple of days to get that under your belt. But most of this should have been pretty simple. And the only last thing I want to point out is what's a very common way to lose credit on probability questions is to simply not show your work. Now, this means things like the better and more clearly you can communicate, the better. So again, show all of those fractions. Even if you want to put your final answer as a decimal, then you should still show your work as fractions. Okay, on the next page, I have a question about what is a conditional probability. And even this, although nominally it's a new concept for today, is not something new because it's something we have been doing, and we just did 2 examples of that on the previous page. A conditional probability is a probability that one event happens given that another event is already known to have happened. So what is the probability that someone uses Macintosh computers given that you already know that they are a graduate student? Now, you just need to remember it's not going to be out of the whole. You're just going to focus on the particular row or the particular column or the particular circle that represents the event that you already know has occurred. So a quick example of this using a Venn diagram, because I suspect that a lot of you guys were using the table for the previous example, is this one here. We have residents of a large apartment complex, and some of them read USA Today and some of them read the New York Times. A represents people that read USA Today. B represents those that read the New York Times. So my question is, what's the probability that a randomly chosen resident who reads USA Today also reads the New York Times? So it's not out of everybody. It says residents that read USA Today. So I'm not going to consider out of everybody, I'm just considering out of this circle. So this circle represents those that read USA Today. So out of people that are in this circle, out of those people who read USA Today, what's the probability they also read the New York Times? So this, again, is a conditional probability. To get it, I'm going to consider what's the probability that someone reads USA Today and the New York Times out of everyone that reads USA Today. Now I'm going to be looking at the entire circle. There's 40% probability of being in the circle, and then there's 5% that you're going to be reading USA Today and the New York Times. So it's going to be 5% out of the 40% that are in the circle. Again, it's not 5% out of everybody, it's just out of those that are already in that particular circle. So again, that's going to be 5% out of 40%. And this is the one exception to the rule I said about you don't have to simplify fractions, you don't have to reduce fractions or anything like that. You're going to want to not mix fractions and decimals in the same answer. So if you're pretty good with fractions, you've already seen that that is equivalent to 1/8, 5 out of 40. Or you can express it as 0.125 or 12.5%. Now, the conditional probability formula isn't really so much a formula, and again, it's not anything we haven't already done before. Formally speaking, the probability of A given B is going to be the probability of A and B divided by the probability of B. Or as I like to think about it, it's the probability that both of these things are true divided by the probability of the thing that you know that is given is true. So again, it's the probability of both divided by the probability of the given thing. One thing I want to mention is that remember, in the case that events are independent, if A and B are independent, the probability of B given A is the same as the probability of B, and the probability of A given B is going to be equal to the probability of A. So remember, in the case that these are independent, that number is just going to become just plain old probability of A. All right. I have a quick check for understanding problem here, so now's a really good time to pause the video. Go ahead and do this example completely. It's a little bit review of independence, and then come back to check your answers in just a second. In this problem, it says we've considered the event A being the student has allergies and F being the student is female, so I'm going to go ahead and put that on here so I don't forget that. So A represents they have allergies, F represents they are female. It's also going to be a lot easier to answer this question if I have some row and column totals as well as the total, which is going to be 40. So part A is find the probability of A. So find the probability that a random student from this sample is going to have allergies. So there are 23 total people. There are 18 total people who have allergies out of the 40 people in the sample, so that's simply going to be 18 out of 40. And again, you do not need to reduce your fractions. Part B, find the probability that someone has allergies given that they are female. So there are 10 people who have allergies and are female, and there are 23 people who are female. So the probability that someone has allergies given that they are female, I'm going to count the number of people who have allergies and are female out of just those that are female. The second part of that asks, find the probability that someone is female given that you know they have allergies. So now my world is not going to be the column of people who are female, but the row of people who have allergies. So out of these 18 people who have allergies, how many are female? So the probability that someone is female given that they have allergies is going to be 10 out of 28. Remember, it's going to be both over given. And here the thing that's changing is the thing that's given. Finally, part C, are the events A and F independent? So to check that, one particular way you could check that is to see, is the probability of A equal to the probability of A given F? So those are actually the answers that we found in Part A and Part B. So the probability of A, we said was 18 out of 40, and the probability of A given F was 10 out of 23. It's probably pretty difficult to see just at a glance how different those numbers are. So a lot of you guys are going to want to stick these in your calculators for easy comparison, and when you do that, you're going to see that no, in fact, these two numbers are not exactly the same. So my answer would be no. Now, some people, again, will ask, well, how different is different? Because, again, it does say that this is a sample of 40 U.S. high school students. And yes, it's true that these numbers are not the same, but maybe you think, well, you know, we could have just gotten an unusual sample. These numbers are pretty close. How different do they need to be? And of course, you guys know by now, if I actually wanted to answer that question for the population, because again, this was a random sample of U.S. high school students, just 40 of them. But if I wanted to see if this is true for the population as a whole, then what I would end up doing is I would say, all right, these numbers are not the same, but I want to say, are they different enough to be statistically significant? And for that, of course, I would be doing a chi-square test for independence to see if these two things are actually independent. Can I make a conclusion about the population? However, that's not what they're asking us to do here. They're just saying, in this sample, are these two events independent? And that's the work that I've shown here, and the answer is no. If they asked me to answer the question for the population, then I would have to go and do a chi-square test for independence. And finally, it says explain your answer, so give a little bit of explanation of what's going on. And I just said, well, if these two events, A and F, were independent, the probability that someone has allergies and the probability that someone has allergies, given that they are female, should be equal. Since they are not independent. And that's all it is. Pretty much the rest of this is going to be, again, me running through examples and asking you to pause. So let's go ahead and go to the next page. It starts off asking you about the general multiplication rule, which should look really familiar. If you haven't already, please make sure you have your formula sheet out and you're referring to it, that you know where to find these things. Please actually use your formula sheet, for the love of God, when you're doing your work, whether it's, you know, these class examples or whether you're working at homework problems, because you need to get used to what's actually available on your formula sheet, not what is on your notes. Do your best to do your homework or practice problems with just the resources you will have on the actual test. So the general multiplication rule is just this. The probability of A and B is equal to the probability of A times the probability of B, given that A is true. This should look really familiar. If you look on your formula sheet especially, you may have noticed that there's a bit of multiplication going on. But yeah, this is something you don't actually need to memorize. You do need to understand these symbols really well, because otherwise this formula sheet is going to be less than useless to you if you don't actually understand what it's trying to tell you. Now remember, there is a special case. The probability of A and B is equal to the probability of A times the probability of B given A is always true. But in the event that A and B are independent, remember that the probability of B given A is exactly the same as the probability of B. So this is just going to become the probability of A and B is equal to the probability of A times the probability of B. That's not the definition of independence. Remember, the definition of independence: two events are independent if and only if the probability of A is equal to the probability of A given B. But this is a consequence of when things are independent. Don't forget, the other rule that's on your formula sheet that you need to know is the addition rule, which looks like this, which we've used before. The probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. Remember, that's just saying it's a probability of A plus a probability of B minus those things that just got double counted when you did A and B together, when you added A and B together. There is also a slightly different thing, again, when two events are mutually exclusive or disjoint. If A and B happen to be mutually exclusive, then that means that A and B cannot happen at the same time. That means that last term in the general addition rule, the probability of A and B becomes 0. So the probability of A and B is 0, then it just becomes the probability of A or B is equal to the probability of A plus the probability of B, because there is no overlap. All right, let's run through a bunch of examples now. If two people are selected at random, find the probability that they were both born in January. Now this is a seemingly very simple question. However, there's a really important assumption that we're making here. In order to answer this question, we kind of have to assume that these people are independent. So assuming these people are independent, the probability that they were both born in January is going to be equal to the probability the first one was born in January times the probability the second one was born in January. And we're going to be assuming that they don't affect each other, so the probability that the second person was born in January, given that the first person was born in January, does not change. They're all just going to be the probability that a person is born in January. Assuming that people are equally likely to be born on any date of the calendar, that's going to be something like 31 out of 366 or 31 out of 365. The second question here, if the probability of a certain pill being effective is 0.95, find the probability that it will be effective in each of 60 independent applications. So the important word here is independent. That means it's not going to change. Whether or not the first application was successful or not doesn't change the probability that the second or the third or any of the other ones is going to be. So it's going to be 0.95 each time. So the probability it will be effective in each of these 60 is going to be the probability of it being effective in the first times the probability it will be effective in the second times the probability it will be effective in the third. So it's going to be 0.95 times 0.95 times 0.95, 60 times. So in math shorthand, we're just going to use some exponents to make that a little bit shorter and say, all right, that's going to be 0.95 to the 60th power. That's going to be a little less than 5%. Next example. Miss Lee has only a few pieces of candy and wishes to distribute them randomly to the class. She puts everyone's names in a hat to do a raffle. What's the probability that you will win on the first draw or the second draw? So we're going to start and we're going to say, all right, well, here's you. And on the first draw, this first branching represents the first draw. One of two things could happen. You could win or you could lose. Now it says, let's just assume that there are 18 people in this class. We're going to assume it's a small class. And if everyone's in class, then, it might be 18 people. It might not be 18 people. But the probability that you win is going to be 1 out of 18 then. And the probability that you do not win is going to be 1 minus that, which is going to be 17 out of 18. So the probability that you win on the first draw is 1 out of 18. The probability you do not win on the first draw is going to be 17 out of 18. Now, on the second draw, one of two things could happen. You could win or you could lose. So you could win or you could lose. You could win or you could lose. The probabilities that go on here are going to depend on whether or not you're doing this with or without replacement. So since we already did a couple of examples previously on this page where they are independent, that is, they did not change, and the same thing would happen here. So if they were independent, the probability you win or don't win on the second draw is going to be exactly the same as it was for the first draw. Since we just did those, we're going to assume for the purposes of this example that we're doing these without replacement. So if you're doing this without replacement, and you won the first time, then the probability to win the second time is going to be 0. You cannot win on the second time because you've already won, which automatically means the probability that you do not win is going to be 1, and the probability that you do win is going to be 0. But let's say you lost on the first draw. Well, two things are going to happen. First of all, you still have a chance of winning, so that probability that you win the second time is not going to be 0. The probability that you win or lose, though, is now not going to be out of 18, but out of 17. Because if it was done without replacement, there's no longer 18 in the pile of tickets to be drawn. There's 17 left. Your chance of winning is now going to be 1 out of 17. And the probability that you are not going to win is going to be 1 minus that, which is going to be 16 out of 17. So to answer the actual questions, what's the probability you win on the first draw? Well, that's going to be pretty simple because the probability you win on the first draw is just that first branch on there, which is going to be 1 out of 18. So the probability you win on the first draw is just 1 out of 18. The probability you win on the second draw, though, and again, we are assuming this is being done without replacement. Well, the probability you win on the second draw is going to be represented by the I guess you could see the third branch down, which means you'd lose the first draw, but then you'd win the second draw. So you're going to lose the first draw, that's 17 out of 18, times you're going to win the second draw, which is going to be 1 out of 17. And those of you that are relatively good at manipulating fractions will notice that, hey, those two 17s are going to cancel out when you multiply these. So your probability you win on the second draw is going to be 1 out of 18, which is exactly the same as the probability you won on the first draw. And this actually seems a bit unintuitive. The probability you won on the second draw is exactly the same as the probability you won on the first draw. And the way to make this make sense is to say, all right, well, let's extend this. Let's say that we did 18 draws. Well, if we did 18 different draws, then the probability that you win eventually, if we keep going, is going to be 1, because at some point your name is going to be drawn. If we assume that we're going to do this 18 times, then it's not so much a matter of are you going to win, it's going to be, well, which draw are you going to win on? So everybody is going to have the same chance of being drawn for any particular one of those draws. Alrighty, that's long enough for part 1. Part 2 is going to be shorter. Go ahead and join me over in part 2.